All right, this is part two of successive substitution method to find the root of a function in MATLAB. So we talked about how we can write a script. This is the function in which we basically cycle through x equals g of x. So we talked about how we can write the headers. We use fprintf function in MATLAB. /n means new line, which means basically you leave a blank line in the command window. And then you're going to write these as the headers of the table, and then you put some lines under, well, basically these are going to be the underline for the headers. So then we go to the plot window, and we're going to plot our initial guess. So our initial guess is going to be x, right? So we take it from the argument list, we evaluate g of x, and then we plot that on figure 1. On figure 2, we're going to plot x and f of x, or f of x against x. Again, we're going to use a black dot. Marker size is 40 here, 40 here, so it's rather big dot. So if I put a breakpoint here and run the code, you should see. So this is window 2. This is window 1. And you see that this is the initial guess. It's a black dot right here. So this is g of x, this is y equal x, and the intersection is the point where the 3 points that intersect. 1, 2, 3 correspond to 3 points here. There's 1 point here. The root meets difficult to see. There's another one here, and then the last one is right here. So 3 points or 3 roots. Let's say which one we're gonna target. So we're gonna check the initial. Well, we're gonna check the error. And the error is the difference between x and g of x. If these two are equal, then that's going to be the root, but because they're not equal, the difference is going to be the error. So if the error is bigger than the epsilon, we have to cycle, we have to iterate. If the error is less than epsilon or equal to epsilon, we're going to break and we stop iteration. Every iteration, I'm going to keep the number of steps. I assign g of x to x. I find the error, which is the difference between x and g of x. So this is the new x. I evaluate with this x, I'm going to evaluate g, right? Because I know what g is. G is given by the argument, and that is corresponding to the second argument, which is 1 over 10x. Okay. After I calculate the error, then I can print out the number of steps, x, g of x, f of x, and error exactly on the bar below these headers. Yeah, below these headers. Okay. So now about the format. So a few things about this. I'm printing the number of steps as an integer. So this percent means exactly at this location. Print a number. 4.0f means use a float representation for float number, but then use 0 number of digits and total 4 digits. Okay. Then leave some space here and then print the next number where this percent symbol is to print the next, which is the x value at every iteration. You're going to use 11 characters or 11 spaces for x value. You're going to use scientific form. That's what this e means. And then within this 11, with these 11 spaces, you're going to use 4 decimal digits, and the rest will be, spaces for the exponent, for the decimal point, and for the integer part. Okay, so we're going to use the same format for the other 3, for g of x, f of x, and error. Okay, so once I've actually print, let me just actually print. Okay, so here's actually, I did the problem. I ran it all the way through, and you see that, okay, these are actually scientific form. So totally there should be 11 spaces from here to maybe even further down there. Okay, so we have 4 digits for the decimal, and then 3 digits for the exponential. So this 4 comes from this 4, total 11. If we count, there should be 12, well, it should be 11 from here to here. And And yeah, so that's what the format means. If the number of iteration reaches the maximum number of iteration, and we didn't find, or we couldn't find error to be less than epsilon, then we're going to basically raise this error statement saying that the maximum number of iterations has reached and we never converge. So we're going to quit the execution. Okay, so if we quit execution, we set flag 1. If we do not basically hit maximum number of iteration, then flag is going to be still 0. Okay, so this flag 1, 0 or 1 is to check whether we meet the condition or not. Okay, the condition of maximum iteration, or the number of iteration is less than or equal to the maximum number of iteration. If this condition is satisfied, then flag is 0. If this condition is not satisfied, which means number of steps is equal to the maximum number of iteration, then the flag is going to be the 1. And as soon as flag becomes 1, we cannot basically plot x and f of x as a red point on the curve. But if flag is still 0, which means we didn't hit the maximum number of iteration, then we can basically point or locate this point with like red dot on the curve. And you saw that, actually let me run the code completely. So get rid of that and continue. Get rid of that one and continue. So you see that this red dot shows up here. This is initial guess. This is final result. And actually that is the root. So if you zoom in here, you see that's exactly where the curve actually hits the x-axis, right? This is the x-axis, you see that, and the curve hits there. So anyways, that is the solution. Okay, and yeah. So, okay, so that was successive substitution. Let me see. Okay, there are certain things that we need to know about successive substitution, and that is the starting point is very important. An example is, imagine we want to find the root of this function, log x plus 1/2 exponential minus x, and then plus 5 or 2. Okay. Now, if you plot this function, well, the log function actually looks like, the first part of it actually looks like this. Okay. Now, imagine you use initial guess right here. Okay. And so if you want to solve this problem using, let's say, Newton's method, so right here, when we have initial guess, we're going to draw the tangent, and wherever tangent hits the x-axis is going to be the next point. Now in this case, we draw the tangent, it hits the x1, but the x1 is supposed to be on the left side of the x-axis, which means negative. So x1 is going to be negative, right? Then if we use x1 in this function, right, then, or basically assume that our g of x, well, actually focusing on Newton's method, if x1 is going to be our second guess, then we're going to have a problem because x1 is negative, and next time we want to evaluate this f of x, we run into a problem because log of a negative number does not exist. Okay, so that is the problem with Newton's method, and the reason is our guess was too far from the solution. If this is the solution, you start the guess point here. In the next step, Newton's method is going to diverge, right? Because x is going to be negative, right? And log of negative number does not exist. So that means initial guess should be very close to the root, to the exact solution with Newton's method, especially for this function. All right. So this actually tells us if you have crazy function like this, which is really nonlinear, then we better linearize the problem. Okay. So here I'm going to talk about some sort of linearization. Assume we have a function like that, it's sum of exponentials, and I have the constants a and b and c and d tabulated here. So I have 4 constants a, b, c, d, okay? And because in this sum I have 4 terms, I have 4 sets of a, b, and c, and d, okay? Now, imagine the variable here is t, and I want to find t such that it makes this thing equal to 0. Okay, the sum of the exponential minus 1 equal to 0. Okay. Now if you go ahead and plot the function to see, where the root is, I have it here. Okay, so the function is this one. So this is the function. You see that it's actually going up very fast. So here's my x ranging from 250 to 450, and then my f of x varies from, let's say, 0 to 400. So this is a rather large range, and if you want to do something like Newton's method or other methods, we better use more linear function than nonlinear. Nonlinear causing Newton's method really to diverge, because the initial guess can lead to numbers like that when we talk about log of x, and basically becomes undefined. Okay, so because of that, it's always good to linearize a problem. So linearization should be in a way that it actually makes the range of variation smaller, right? Like in this case, my f varies from 0 to 400 and x varies from 250 to 450. So linearization should be in a way that actually changes these ranges. Okay, so the first step for linearization is we're going to move this one to the right side. Okay, so imagine f of x equal to 0, right? And I can add 1 to both sides, or in other words, we can move 1 to the right side, and then take the log of both sides. Then we get this log of this sum is equal to 0. Okay, so now if you go ahead and plot this function, log of something equal to 0, right? Then we get the second window here. So now look at that. So the range now varies between 10 to the minus 3 and, let's say, 3. So between 3 and, let's say, 0. So we change the range to compare these two. Okay. We change the range of y-axis from 0 to 400 to something, let's say, between 0, let's say down here is 0, to 3. So 0 to 3 compared to 0 to 400. So you see that we actually changed the range quite a bit. We can actually go even further and do a better job by linearizing even the x-axis. So in this case, I know that my temperature varies from 250 to 400, but if I get the reciprocal of the temperature, which is 1 over t, okay, then the x also varies in a small range. And if you do that, then temperature, which is going to be 1 over x, or t is equal to 1 over x, then t varies, or actually 1 over x, or basically 1 over t, yes. So 1 over t is going to vary, from 2.2 to maybe 3.4. So contrast this range, 2.2 to 3.4 raised to 10 minus 3 power, right, compared to 250 to 300. So you see that actually we changed the x-axis range a lot. So as a result, the function looks like actually a very linear function. Now if you use this in Newton's method or bisection or secant, convergence will be much faster. Maybe in a couple of iterations you converge, and if you don't do this, if you don't linearize it, then convergence would be maybe, I don't know, 10 steps or 20 or 50 steps. So it's going to take much longer. Okay, so yeah, so that's about this example. Let's go ahead and actually run this code completely all the way to the end. So I'm going to clear this breakpoint and continue. Oh, there you go. So this is the root, the first root that I found. And yeah, and how many iterations? Well, look at the table. Just 4 iterations. We find the root of that, exponential of, something with like 3 or 4 terms in the summation, which was actually rather nonlinear. By linearizing it, actually converges them really fast. Okay, so, okay. I hope you enjoyed this video. Thank you so much for watching. Stay tuned for the next part of root finding in MATLAB.